So sampling question, N3 minus, so overall minus 1 charge. What are some resonance forms? So let's just draw a possibility, then kind of go from there. So nitrogen wants to have how many bonds? 3, right? So everybody's not going to be happy here. If I did this, I would have a negative charge here, right? I'm assuming full octets. I would have a plus charge here.
I don't know if it's just my screen, if my computer's slow, but I can't.
Okay. So negative charge, 2 bonds, full octet, nitrogen. Plus charge, 4 bonds, full octet, nitrogen. 2 bonds, full octet, negative charge. So this is a possible resonance structure. What else do I need to check? I need to check to make sure I balance my charge, right? So overall, is there a negative charge? Overall, there's a negative charge. This is a possible resonance structure. Resonance arrow. How can I move electrons? I can move electrons from the end. Lasso them, right? Grab them both. Move them here. Make a bond, break a bond, move those there. What would that give me? Take a second and see if you can tell me what that'd give you. So we numbered our atoms, nitrogen 1, 2, 3. Electrons come here, form a nitrogen pi bond between 2 and 3. Pi bond between nitrogen 1 and nitrogen 2 breaks. Those 2 electrons go to the nitrogen. Now it has a negative 2 charge for 1. 2 has a plus charge and 3 is neutral. Which one's a better resonance structure? Which one's the major resonance structure? So the first rule, of course, is the octet rule. Are we good with the octet rule? Are we good with the octet rule for this? Yeah, we're good either way. So now what do we want to look at? Maybe charges. You know this from Gen Chem. You want lower charges or higher charge. -1 is better than -2, right? So lower and higher is a hard one to deal with these, right? So the second one is not as a major resonance contributor. It's less likely, right? And the other sampling, they also gave you ones that were just not the same structure, had different charges. So that's wrong. One last thing, take this to another level. Nitrogen number 2, what's the hybridization state of nitrogen number 2? What would his hybridization state be?
SP.
SP. What about the hybrid? That's right. What about the hybridization state for nitrogen 3?
SP2.
Yeah, it's the Wenzel curveball. Is it SP2? It's SP3. Excuse me. It's SP. Right? This nitrogen's SP. It's going to do resonance. That lone pair is going to do resonance here. Right? So it's going to choose to be SP, so that this lone pair is in a p orbital. Right? It's actually SP. They're all SP hybridized at some level. So they have methylamine here, and they say, what's the conjugate base? So this is good. This leads us into what we're going to talk about today a little bit. What do bases do? So if we're asking for the conjugate base, that means this methylamine, let's say it reacts with, I'm just going to draw a generic base. Right? It's going to react with the base. That means this is an acid. If we're drawing something's conjugate base, on the other side of the equation, it's an acid. So where is this acidic at? Now, acidic can mean a lot of things. The classic acidic sense in organic chemistry is a delta plus electron deficient hydrogen. You also have Lewis acids that are electron deficient just atoms. Okay? This is a Bronsted acid. So Lewis acid is the big umbrella, right? Lewis acid just says an atom's electron deficient. One type of Lewis acid is a Bronsted acid. It has only to do with, Bronsted acids have only to do with hydrogen. So all Bronsted acids are Lewis acids. Are all Lewis acids Bronsted acids? No. Same with Lewis bases. Lewis bases is the big one. A Bronsted base it's a type of Lewis base. All Lewis bases aren't Bronsted bases. Bronsted only has to do with hydrogen. That's it. But everything's a Lewis acid or base, right? A Lewis acid, electrophile, Lewis base, nucleophile, right? We know those terms. So in this case, if it reacts, acid-base reaction, what would the conjugate base be? It'd be a nitrogen with a negative charge, and then we made H base. So this is a reaction, a Bronsted acid, Bronsted base reaction. This is the conjugate base, right? Overall, we balanced our charge. There we go. So for this one, resonance structures, all of these atoms are part of the p orbital system. They're all going to be delocalized into this system. This oxygen is going to be sp2 hybridized. So one of its lone pairs will be in a p orbital so it can do resonance here. Same with this one. Numbering the atoms really helps. All right, we've identified the atoms are going to be in the p orbital resonance delocalized system. Now it's just a matter of practicing and drawing them. So one I think people miss, the easiest one, and if you go back and look at your notes, we did some of the classic ways resonance structures move. That's like class notes number 2. So one of the easiest things to do is just a one arrow thing where that pi bond breaks and those lone pairs go right to that nitrogen. And this is usually the one folks will miss. What am I missing? What do I need to do still?
Lone pair and then double bond with carbon
Lone pair where?
on nitrogen.
Lone pair on nitrogen. What else am I missing?
Carbon has 3 bonds and it's supposed to have 4, so you bond it with one of the oxygens.
But it's not. So it should be. But just by looking at the arrows I drew here, where should I put a plus charge?
On carbon.
Right. So this is the one people usually forget. So there should be a plus charge on 2. And then you're absolutely right. Then you have 2 more resonance structures where the lone pair from oxygen 4 could come here, or the lone pair from oxygen 3 could go there. So I think that's what they're looking for. So this is called an imidazole. The question I have for you is the nitrogens. What hybridization state is nitrogen? We'll call it nitrogen 1 and then nitrogen 2. What hybridization state is nitrogen 1 and what hybridization state is nitrogen 2? So take a second and think about that. Nitrogen 1 is sp2. sp2 hybridized, there's a box. Now notice how that's different than the azide one. Why is that different? Because that was a sp, well, we could be an sp2 next to an sp, right? So be careful. That's a little different. What's the hybridization state number 2?
Isn't it also an SP2?
It's also sp2. Awesome. Good, right? It's sp2 because it's next to, right, this lone pair wants to do resonance, right? If you can do resonance, you want to do resonance, right? So that makes this nitrogen going to choose to be sp2, have a p orbital, and be able to do resonance here and resonance here. All right. Those are the hybridization states. What's the hybrid orbital this lone pair lives in? What hybrid orbital does this lone pair live in? And what hybrid orbital does that lone pair live in? Take 30 seconds to think. And so if something's sp2 hybridized, you know the hybrid orbitals are. There's a p orbital. And then there's a sp2, an sp2, and an sp2, right? Those are the hybrid orbitals for that hybridization state. What orbital is that lone pair in of these 4? 50-50 shot. Throw it in the chat. Guess. So this lone pair nitrogen 1 is in an sp2 orbital. How did I know that? This nitrogen's sp2 hybridized. Look at its bonds. It has a sigma, and a pi bond. If you have a pi bond, you must have what? Show them to me. A p orbital. If you have one pi bond, you only have one p orbital, unless there's something else going on. So this lone pair is actually in an sp2 hybridized orbital. So it's not part. This is not delocalized. It's not part of the resonance. It's actually 90 degrees away, right? If you look at an sp2 hybridized atom, it's 90 degrees from the p orbital system. What about number 2? Now is that p or sp2? Where's that lone pair at? Then essentially what I'm asking you is, can this lone pair do resonance? Is it delocalized? Go ahead and throw it in the chat. So nitrogen 2, lone pair, is it p orbital or sp2 orbital? So the answer is it's in a p orbital, because this one can actually do resonance, right? This lone pair can't. Now, if you're still having confusion on this, go back and look at those the hybrid orbital diagrams where they actually show the actual structures and the things and the orbitals in that hybridization tool. That'll help you see this a little better, right? There's a couple good pictures in the book as well, but we'll keep talking about this as we keep coming up, okay? Bonus question. Which one's more reactive? This one, this lone pair, nitrogen 1 lone pair, nitrogen 1 lone pair, nitrogen 2 lone pair. Which one's more reactive? Say it again. Nitrogen 1 lone pair in an sp2 orbital is more reactive because it's localized. It can't do resonance. This lone pair is doing resonance. If it's doing resonance, it's going to be less reactive. It's more stable. So actually nitrogen 1 is more basic. It's more nucleophilic.